So today's class, we're going to be talking again about 7.8, and I'm hoping that we'll be able to get into and spend a little bit of time in 7.5 as well, strategies for integrations. But we also have Friday's class to talk about that, and it's largely a review section, and then we also have a review day on Monday as well. So I'm not going to be too concerned if we don't get to spend a lot of time in there quite yet. Last class we left off, we were doing this problem here, which combined together partial fractions along with one of these improper integrals. And so we had to spend a while, and kind of all of this work over here in the green. On the right-hand side is just how do you find the antiderivative, forgetting about your limits of integration, right? And so we spent some time using the partial fractions. We did a good partial fractions decomposition. We rewrote this, and then we had to go and integrate all of those pieces. And we left off last time saying that the integral of the 1 over x plus 4, that's going to be equal to this natural log of the absolute value of x plus 4. This one required u sub, and this one is going to be an arctangent sort of function. So if you go ahead and evaluate using those techniques for the u sub and the arctangent, this is what our final antiderivative would look like. And of course, we can take the derivative of this and get back to where we started. So that's the first bit. Now we have to spend some time evaluating out with our bounds. And in particular, we'll incur a limit, right, as t goes off to infinity, and we'll need to think a little bit about this. But that's kind of a quick review of where we were. I see there's a raised hand, so why don't we go ahead and call Jenna, you've got the floor.
Hi, can you hear me?
Yeah, sure can.
I was wondering why, like how you knew to use arctangent and a u sub to find the derivative, like how you got to that spot.
Yeah, so this quite often happens when you have one of these irreducible quadratics, something that looks, kind of the classic ones here would be something like x squared plus 1, x squared plus 4, stuff like this. We saw that, splitting this up, right, when we think about how do we integrate this thing, I think it's still quite difficult. And so we split up this fraction across the numerator, right? We have this common denominator, and we just kind of split this up, negative x portion and the 4 portion. And now when we look at this, right, this should look very familiar from our chapter 6 days, right? That this looks like an arctangent. Remember that the derivative of arctangent is this 1 over quantity x squared plus 1. And this actually comes back from our calculus 1 days. We were able to integrate stuff like this using just u sub. And so once you know to break them up, I think it's considerably easier. But yeah, you do have to kind of look at this thing and say, well, how do I, now integrate this thing? So yeah, splitting them up is going to be the key. Does that kind of make sense?
Yeah, thank you.
Yeah, of course. Okay. So let's see here. I started to plug in some specifics, right? So once I found the antiderivative of all this, I went ahead and, right, we need to plug in 0 to t. Remember, our improper portion of this comes from the fact that we're integrating to infinity. And so we're going to have some limit as t approaches infinity of this integral evaluated from 0 to t. And so, okay, I know my antiderivative now. I can plug in 0 and I can plug in t. Here's what it looks like when I plug in t, right? Basically just everywhere you saw an x before, now you see a t. And when you plug in 0, right, you have to be a little bit careful with this, but sure, right? If you plug in 0 in for x, you would get the natural log of 4 for the first bit. If you plug in 0 for x for the second bit, you're going to get the natural log of 1, which is of course just 0. So that's where this 0 is coming from. And tangent inverse of 0 is indeed 0. And so that's just me evaluating out when, x equals 0. So now we're to the final bit where we need to evaluate with this limit, right? The limit as t approaches infinity. And so we have to be a little bit careful with this. One thing that I know for sure, and so I evaluated down here, is that arctangent as t goes off to infinity, arctangent has an asymptote at pi over 2. It's the exact same reason kind of that regular old tangent, right? If I was to just draw a quick picture of tangent of x, remember that this kind of looks like this function here. And when you divide by 0, you have some vertical asymptotes. And those happen at negative pi over 2 and pi over 2, exactly when cosine, what you're dividing by, ends up being 0. So when you do arctangent or tangent inverse, remember these things are kind of flipped. We still take this one restricted branch of tangent and we flip it across the line y equals x, and you get something like this. And of course, remember when you go and you actually evaluate this out, right, you swap all of your x's and your y's. And so before you had an asymptote at x equals pi over 2. And so maybe it's not surprising at all that when you swap your x's and your y's, you get now an asymptote at y equals pi over 2. And so this is just a quick reminder of what tangent inverse looks like. I know this is a bit of a review from our chapter 6 days, but I find that some folks maybe have forgotten this. And so yeah, as you go off to infinity, right, tangent inverse gets closer and closer to its asymptote, its horizontal asymptote, pi over 2. Still, what I haven't evaluated out here are these two pieces right here. And when I do this, if I just try to plug in infinity, right, everywhere I see this t, right, I would have the natural log of infinity, which as you get larger and larger values inside of your natural log, this does go to infinity, albeit a bit slowly. And then for this second bit, same thing. If you take a very large number, you square it and you add 1, still you have a very large number. So you're plugging in essentially infinity into this thing. And so the natural log of infinity is still a very, very large number, infinite. And so we end up with infinity minus infinity. And so what is, I guess the question that I want to pose to you guys is, what is infinity minus infinity? Yeah, I see you guys are seeing the problem with this, right? Yeah, like depends how big they are. Yeah, that's true. So yeah, this is one of these indeterminate forms, right? And so we need to figure out, right, maybe how can I rewrite this in a way that I can actually figure out this limit? I'm hoping that maybe I can use L'Hopital's rule, right? But L'Hopital's rule requires it to be written as like a fraction and everything. And so, yeah, we need to spend a little bit of time. Maybe I'll pull off one more time to the side here. And I'm going to write this problem piece here. You can see kind of a good trend that anytime I come up against something hard, something complicated, sometimes I like to make a little sub-problem here and just kind of stare at this issue, straight on. And then once I have the result, I can plug it back into the overall story. So the question is, how do we evaluate this thing? And in particular, we'd like to use maybe L'Hopital's rule because it is one of these indeterminate forms. And yeah, it looks like some folks have some good ideas here as far as how we could maybe do a rewrite. So what I see here is that the fact that we have two natural logs being subtracted, I'm very interested in then using the quotient rule, because the quotient rule for logarithms will allow me to write this in terms of a quotient. The only thing that's stopping me is this darn 1/2 power. Right? With the quotient rule, you have to have ones in front of both of your natural logs. And so maybe the first thing that we would want to do in order to rewrite this is to absorb that 1/2. And when I say absorb that 1/2, remember you're allowed to take coefficients and rewrite them as powers. So raised to the 1/2 power, that'd be the same thing as the square root. Notice that I'm plugging in very large numbers. So really these absolute values aren't going to be doing a whole lot. I'm probably going to stop writing the absolute values because again, we're plugging in large t values as t goes off to infinity. So like 1,000,000 or 1,000,000,000 or something like this, right? And so yeah, all of this is going to be nice and positive. And so now that I've went ahead and I've used the power rule here, now I've gotten rid of that 1/2, and now my original idea of trying to use this quotient rule will work out for us. So this would be t plus 4 divided by the square root of t squared plus 1. Again, everything's nice and positive here. And so, okay, we kind of have a fraction. The problem that is it's trapped inside of a natural log. Well, luckily we saw in class several times, when we were using the L'Hopital's rule sort of stuff, that there were some cases where you were allowed to push your limit inside of a function. And just look at this bit here. So I'm going to go ahead and push my limit inside of my function. Does anyone remember what was the condition? When are you allowed to actually do this? You can't do this for any old random function, but you can do it many times for many nice functions. And yeah, so it has to be a continuous function. So the fact that the natural log is a nice continuous function, right? That when you draw it, you don't have to pick up your pencil or anything like that. That is what allows you to push limits inside. And so now you can see we've simplified things and we have this nice quotient, right? It's in a fraction form. It's in one of these nice infinity over infinity forms. Sorry, I forgot to include my limit here. This is technically an incorrect statement. So let me rewrite this limit as t goes to infinity. Thank you. Oh, no, sorry. My limit's on the inside. I was like, where did my limit go? There it is. The whole thing that I'm doing. So yeah, now we need to evaluate out this limit on the inside. Maybe you've done so many of these that you can guess already. And of course, you could use L'Hopital's rule for this as well. But can anyone tell me what this inside limit is going to be equal to? All right, so I'm getting some correct guesses, but some guesses that are off a bit. And so I think it's probably a good idea if we go ahead and we do this. The answer ends up being 1. And so let's go ahead and evaluate this out using L'Hopital's rule. So I'm going to go ahead with L'Hopital's rule on just the inside bit. So we're still going to have the natural log on the outside and everything. And we're just going to take the result and plug it in here. So if I apply L'Hopital's rule, right, I would need to take the derivative of the top. And the derivative of the top is just going to be 1. And when I take the derivative of the bottom, I have to do a chain rule, right? So there's 1/2 all of this stuff here, reduce my power by 1. And then I'm going to multiply by the derivative of the inside here, which is going to be 2t. And so there's a little bit of canceling that happens here. And oh, this is going to be one where these darn square roots they kind of dance back and forth sort of deal. Yeah, so this is one where we have to put it all inside of a square root. Well, this problem's getting away from me a little bit. I don't really want to do that. So I'm going to I will fill in the rest of the details maybe after class and post them with our notes. But this, again, kind of the L'Hopital's rule isn't going to be the focus of our upcoming exam and everything. And so this is maybe a little bit more difficult than I had imagined. The one way that maybe I could say that I can see this fairly quickly is that, you know, the square root of t squared here is going to be essentially behaving like t. Right? Kind of if you ignore this lower stuff, this 1 right here, this is essentially behaving like t. And on the top, this is, well, again, essentially like t, especially for very large t values. And so you can kind of think of this as, you know, a linear polynomial divided by a linear polynomial. And that's why I can confidently say that the answer is going to be 1 for this limit. And so overall, we'll get that this, once we plug it inside of our natural log here, that this will end up being 0. So all that to say, I see that there's a few raised hands, and I'll certainly give an opportunity for questions here. But let me just write the final answer and highlight it and all that sort of stuff. The final result is, right, this limit of these 2 natural logs being subtracted, this infinity minus infinity, is just 0. And so plus, let's see, our 2 pi minus the natural log of 4. And so our final result here, 1/17 times 2 pi minus the natural log of 4 is the end of this problem. Finally. All right, so let's see what kind of questions we have out there. Ajuan, you've got the floor.
All right, can you hear me?
Yes, sure can.
All right. So I had a quick question on the black part at the bottom here.
Yeah, of course.
So that last line, limit to t goes to infinity, ln right there. So what made you? Well, I'm seeing. How did you know that you had to write it as ln t plus 4 over square root t squared plus 1.
So remember, anytime that you have an indeterminate form that you're trying to apply L'Hopital's rule to. So in this case, our indeterminate form was this infinity minus infinity. If you want to apply L'Hopital's rule to this, right, you have to rewrite it so that you have a fraction form. Remember, L'Hopital's rule only works when you have, this quotient, this f of x on top and this g of x on bottom. And so if we wanted to have any hope of applying L'Hopital's rule, we have to somehow rewrite this as a fraction. And so that's kind of what set me down this path of trying to do a rewrite in a way that we got a fraction. Does that kind of make sense?
I'm still a little confused, but I know you probably had class, probably got more time to do it in office hours.
Yeah, maybe office hours would be a good time for this, because this again is L'Hopital's rule, which will not be the focus of our upcoming exam. I mean, maybe this is a fairly complicated problem. I'd be surprised if anything was like this on the final exam, but it would be more appropriate for it to be on the final exam, just because, right, the final exam is interested in testing the entire course worth of material, including chapter 6 and chapter 7. Right. So this is a great problem that kind of combines these two ideas, and you see why we have to talk about L'Hopital's rule and how this leads into these sorts of problems. But again, kind of the focus of our upcoming midterm is supposed to be about chapter 7, not so much about chapter 6.
Okay, that's cool. That's cool. Thank you. I appreciate it.
Yeah, of course. Any questions in the Q&A?
Should we expect the question as long as number 4 on the exam?
Oh, okay. So yeah, I think I just discussed this. This is
Oh,
kind of a long one.
Okay.
Here, probably not anything this difficult. I would say that, this one that we did back here, still we did have a small L'Hopital's rule here. This would be maybe more in line of something that I would say is reasonable for an exam. But even then, right, you saw many examples, in the pre-class video notes, and certainly things here that, there are many problems that you don't have to have L'Hopital's rule necessarily. So I would say more like examples 1, 2, 3 than like example 4. Let's go ahead and call on Lucy. You have the floor.
Yeah, so I don't understand. So when you graphed it and you got like that t approaches pi over 2, why didn't you plug that in for t? Like, I'm just confused why you plugged in infinity instead of pi over 2.
So this was only for this single piece right here. I was trying to explore how does this 4 tangent inverse behave as we plug in very, very large values as t goes to infinity for this piece. And so when I get that result, I only plug it in, right, to that piece. So I get the 4 and the pi over 2, but still those other functions, right, these don't have anything to do with tangent inverse. And so the result there is going to be different.
Okay, and then I have another quick question. It's kind of more general.
Okay.
So when do you know to make t approach infinity as opposed to making it approach like 0 from the right?
So yeah, that really has everything to do with the function that you're evaluating, and in particular the limits of integration. So in this case, we have 0 and infinity. Now, 0 isn't a problem point like we've seen maybe in some previous examples, just because remember, we're very interested, these improper integrals come up anytime you either go to infinity or negative infinity, or if you have a discontinuity. And so we checked right at the very beginning, we have a discontinuity at -4, and this one, there's no real values that would make this equal to 0. So our only discontinuity is at -4, and luckily our interval doesn't include that. And so we don't have to be careful around 0. In comparison, like if we go back here and we look at this one from 0 to 8, notice that if you were to plug in 0 into the denominator, right, you'd be dividing by 0, and that makes us have a discontinuity there. And so we have to be careful and, set up one of these limits and all that sort of stuff. Does that kind of make sense?
Yeah, thank you.
Cool. Yeah, no problem. All right, let's do maybe one more here and then start thinking about the next problem, and then there'll still be more opportunities to ask questions here. So Ishwari, you have the floor here.
Hi, Professor.
Hi.
So, so in example for like the bottom black part that we were confused.
Yeah.
So we can divide the numerator by t and the denominator by square root t squared, and then 4 by t and 1 by t squared under the square root will get cancelled out because that becomes 0, and in
Yes.
the end we are left with 1. So is this a correct approach?
Yes, and that's more in line with what we did in our Calculus 1 days. So you could have actually seen this problem and talking about as horizontal asymptotes in Calculus 1.
Right.
Notice in that approach, you never need to use L'Hopital's rule. So there is a way to do this with L'Hopital's rule, and there's a way to actually do this prior to knowing anything about L'Hopital's rule using our Calc 1 knowledge. Yes.
Okay.
All right.
That makes sense. Thank you.
Yeah, no problem. Okay, so I would like to look at this next problem here. And then again, we'll have more opportunities for questions. But we'd like to evaluate out this improper integral here. The integral from 0 to 8 of this, well, 1 divided by the square root of 64 minus x squared, and integrating with respect to x here. And so again, kind of we have to do maybe a little bit of searching. In this case, we don't have any infinities, right? And so you don't get an improper integral from that. However, if you were to try to figure out, right, what would make our denominator equal to 0? Well, if you plug in a 0 into a square root, certainly you would get 0. So if the thing inside of our square root was equal to 0, we would have an issue. And so if you go ahead and rearrange this a little bit, you'll see that you have discontinuities at both -8 and +8. And so this bit up here, this 8 is a point of concern, right? This is a discontinuity in something where we have to set up one of those limits as t approaches 8. And so this is where the improper integral comes from. Let's go ahead and set this up. We're going to do the limit as t approaches 8. And notice, because our interval is from 0 to 8 here, the way that you're approaching 8 is from the left. So it's 8 from the left. So then we're going to do the integral from 0 to t of dx divided by the square root of 64 minus x squared. And now the same thing happens as, every single one of these problems. We need to know how to find the antiderivative of this question here, this integrand. And so we have to maybe pull off to the side if you'd like, or you can just kind of continue just as is, but we need to spend some time trying to find the antiderivative of this. Can anyone tell me, by the way, maybe you already know what the antiderivative of this is just going to be. So I'm going to do the integral of, I'm going to do a little bit of a rewrite. Sometimes I like one on top here. Yeah, so some folks say trig identity. There's going to be something with a sine inverse. That's absolutely correct. And so, yeah, there's going to be, it's something like a sine inverse here, like a sine inverse. Let's see if we can't guess it, right? So I'm going to go ahead. Maybe I remember it's something like a sine inverse, but remember that 64 there kind of ruins things a little bit. I see a lot of folks thinking about a trig sub, and that would absolutely work here as well, right? So you can certainly use a trig sub for this. When you do that, and folks kind of pointed out that maybe you should do something like x is equal to 8 sine of t. Maybe you can see, right, if you were to rearrange this and solve for t, that you would get this sine inverse of x over 8. So sine inverse of x over 8. This is my guess here, right? I'm just going to guess this. And of course, right, if I wanted to double check, well, let's take the derivative of this and see if we get back to where we started. So if I take the derivative of this, I would get 1 divided by the square root of 1 minus our inside squared times the derivative of the inside. So the derivative of the inside, the derivative of x over 8 is just 1/8 here. Let's spend a little bit of time maybe rewriting this and see if this is actually the same thing. Because, right, maybe from this I can't quite tell. Right? I have some folks who are suggesting maybe we need an extra thing out here. Maybe we need like an 8 out here. But it's hard to say at this point. So let's go ahead and maybe do a little bit of a rewrite. I'm going to take this 8 that's on the outside here, and I'm going to push it inside of the square root. So of course, if I wanted to rewrite that 8 on the outside here inside of the square root, I would have to rewrite it as 64, right? Because 8 is the same thing as the square root of 64. We still have this 1 minus, and I could rewrite this as x squared divided by 64 here. And so now when you distribute that 64 to both of the pieces, right? Well, you get the square root of 64 for the first piece. And then for the second piece, the square roots on top and bottom perfectly cancel. And so you just get x squared. And so we can see that actually that this right here is the correct antiderivative, because when I take the derivative of it, I get back to where I started. Now, of course, there's a formula that you can use to, have this memorized and, just use that. You can also use this trig sub, and the trig sub actually isn't so bad. So there's lots of options in order to come up with it. We get this arc sine of x over 8. I'm just kind of doing the bit of a speedier version here just because I know we have a lot more to get through today. So let's go ahead, and the limit as t approaches 8 from the left. And we now know what the antiderivative is. It's sine inverse of x over 8. And we need to evaluate this from 0 to t. So now let's go ahead and plug in our limits of integration here. Oops, that's a sideways 8. So when I plug in t, I get sine inverse of t divided by 8. And when I plug in 0, I get sine inverse of 0. Now, luckily, right, our calculators can tell us what sine inverse of 0 is equal to, and that's just 0. Or again, you can remember maybe some picture or something like this of what sine inverse looks like. And so the question is, well, as t approaches 8 from the left, is there any issue with just kind of plugging this value into our function? So that is, right, sine inverse of 8 over 8. And so if we go ahead and we plug in 8 everywhere we see a t, we get, right, sine inverse of 1. Anyone happen to remember what sine inverse of 1 is? Or some angle where sine is equal to 1. Yeah, so the angle where sine is equal to 1 is at pi over 2. Of course, subtract away 0, you just get pi over 2 as our final result. And so with this this improper integral, it does converge, and moreover, we can say that it converges to pi over 2. And I guess that's something I should have emphasized in my last one here as well, that this right here, it converges. And better yet, we know what it converges to. Let's see, I saw some questions popping up, I thought here. Let's just call on a few folks. Ian, you have the floor.
Hi. I just wanted to make sure that I understood a few things. There's the negative sign by 8 because it's coming from the left, right?
Exactly, right? On our interval was from 0 to 8. And so the way that we're approaching that 8 is from the left. Now notice in this case, well, it does matter. Not, if you can't really approach from the right, because if you try to plug in values that are larger than 8 into sine inverse, right, you're going to end up getting outputs that are larger than 1, right? If you have a t that's larger than 8 and you divide it by 8, you're going to get something that's larger than 1. And the issue with that is, right, sine inverse doesn't make any sense if you plug in values that are larger than 1. And so it's used kind of in a subtle way here that, the importance that we're approaching from the left.
Okay. And then also, I was just confused how you got the antiderivative, but it ended up being the same. Just
the antiderivative, but it ended up being the same.
1 over the square root of 64 minus x squared.
Mm-hmm.
I was just confused how that ended up being the same thing that it was. You were trying to find yeah.
So what I did is that I took a guess, right, that this would be my antiderivative. Really, I should maybe include a plus c here. But it was a guess, right? And so if you're going to guess what an antiderivative is, you should probably check and make sure that you made a good guess, right? There were some folks who were suggesting maybe we should include an 8 out here, or maybe like a 1/8 or something like this. And I couldn't tell for certain, right, if any of those were true or not, right? And so in order to see, right, what my coefficient out in front needed to be, I needed to check. And right, so this right here is just a check. And of course, if this is the correct antiderivative, if I take the derivative of it, I should get exactly back to where I started. And so notice I did get exactly back to where I started. And so I was happy with this as the antiderivative.
Oh, okay. I thought you were saying that was an answer. Thank you.
Oh, okay. Yeah, no problem. And yeah, I saw in chat a few people bringing up as well that kind of a safer way maybe than guessing and checking would just be using one of our, methods. And so in particular, you did this a lot in chapter 6, where kind of you maybe factor out this 64, and then right, the square root of 64 would be 8 and all this sort of stuff. So you could do it in the chapter 6 method and figure out what the antiderivative is in that way. Or you could also use just the trig sub and see this all the way through. And it's not actually so bad. This one, you have to calculate out your dx and all that sort of stuff and be careful. But you can also get it using this method as well. So a couple different options for you. Let's see here. Oh, no other raised hands for, oh no, some just came up, I thought. We'll call on Jeff. You had your hand up first, and then we'll see what's going on in the Q&A.
Thank you, Professor. I just had a question. I noticed that all the time we're getting the perfect square. Is it possible that we'd say get 63 minus x squared under the root?
Yes, and that's a perfect square, but not of an integer, right? So you would just write that this is the same thing as root 63 squared. And so your answer, instead of having like an 8 down here, for instance, it would have a root 63.
Right.
So it'd be a little bit uglier, but I mean, yeah, certainly it's possible.
Great, thank you. I just wanted to be prepared for the exam.
Sure. What's going on in the Q&A, Yuan?
One thing is about the midterm. Are the midterms cumulative negative final?
Well, I mean, math has this nasty tendency of building on itself, right? And so inadvertently, I mean, it's possible that there could be things from chapter 5 and chapter 6, and even certainly prerequisite courses and all that sort of stuff that you need in order to solve the problems here. Things like we saw with integration by parts, that you had something like the integral of x e to the x. Now, within the integration by parts, right, you have to know that the integral of e to the x is e to the x, which is a chapter 6 thing. So you can see the focus for this problem here is integration by parts, but you do need to know previous content, right, in order to confidently say, right, that the integral of e to the x is e to the x. That's chapter 6 stuff. And so the focus will not be about chapter 5 or 6. It'll be about chapter 7. However, there may be some pieces from chapter 5 or 6 that you need to know in order to do these problems from chapter 7.
And several is asking, can we go over comparison theory for 7.8?
I don't think I've selected any problems here that directly use the comparison theorem. And maybe that's a good point, that in the future I should try to do some that require the comparison theorem. We will get more practice with this in chapter 11. We have a lot of comparison theory questions. And so that's really where it gets brought up and emphasized the most, is like 11.4 is about comparison theorems for series. This is something that I'd be happy to go over in office hours or whatnot as well, but I don't have one that I can maybe make up off of the spot here to help with. So that would be my answer to that. Let's try a few of these true false here, and then hopefully we'll have a bit of time to start talking about strategies for integration. And so I have here, if p is greater than 3, then this integral here converges. True or false? And so we can see, right, that the issue with this integral, where we get the improperness, I suppose, from, is the fact that we have this infinity up here. So this is going off to infinity. Still, right, a part of all of these comes down to maybe evaluating out the integral and forgetting about the bounds for the time being. Just right, what is the antiderivative of this thing here? So we first have to stare at this and think about, okay, how could we evaluate out this integral? And right now we know a lot of different techniques of integration and all that sort of stuff. This one ends up being, yeah, U sub turns out to be very nice for this. And if you choose U to be an inside function, like we saw it works out quite often, we would choose probably U is equal to the natural log of X because it's inside of this raised to the pth power sort of deal. So if we take the derivative of this and kind of why maybe you can see that the U substitution is going to work out so well is that you have this 1 over x dx hanging around the problem, right? We see a copy of our du hanging around the problem. So all of this can be nicely absorbed and transformed into, well, we're going to have this 1 over now u to the p, and this 1 over x dx, we can all trade in for just du. And so it nicely, right, we can exchange this. And so now we need to find the antiderivative of this. Maybe a good thing to rewrite this is, whenever I'm doing calculus with these powers, I think maybe having a negative exponent's not so bad, just because now you can clearly see that this is going to be a power rule. So whenever you use the power rule, remember you need to raise up your power by 1. And then you need to divide through by your new power here. So it'd be like this. And of course, you can double check, right? If I take the derivative of this, I should get back to where I started, right? Because if I took the derivative, I'd have to, well, bring my power down and reduce my power by 1. So it'd go back down to just negative p. So here's what the antiderivative of this is. I suppose my last step, as always, whenever you're using a U substitution, we should swap back in. So this is going to be 1 over, and I'm going to write this as 1 minus p. And then we're going to have the natural log of x raised to the 1 minus p. So instead of negative p plus 1, just writing it like this. So, okay, now let's go ahead and evaluate out our specific, with our specific limits here. So we're going to have the limit as maybe t approaches infinity of, I know what the antiderivative is. Here it is. Notice that, you could be concerned for just a quick second that, am I dividing by 0 here, right? But luckily, right, p is greater than 3. So we know that this won't be 1, in which case we'd be dividing by 0 and we'd have an issue. Okay, the natural log of x raised to the 1 minus p, and we need to evaluate from e to infinity. And of course, we're doing this properly. We're switching out that infinity to t and let t approach infinity. So this would be the limit as t approaches infinity of, and we have this 1 over 1 minus p with all of this. And if I plug in t, I'd have the natural log of t raised to the 1 minus p. And then I'm going to be subtracting away, well, the natural log of e is just 1. And 1 raised to any power is just going to be 1. Forgot some parentheses right here because this 1 over 1 minus p needs to be multiplied by everything. All right, so as t goes off to infinity here, the natural log of t is going to go off to infinity. So this right here is going to basically be like 1 over 1 minus p, and we're going to have infinity raised to the 1 minus p. That's essentially what it's going to be like here. So I would say, just looking at this, I'd be tempted to say that this diverges, right? Because who cares about the subtraction by 1 and all this sort of stuff? I would say that this diverges. And so the answer would be false. But sadly, that's not quite right. The answer here does end up being true. Can anyone see where my misstep was in that logic? Why does this end up converging? So no, it's not that this is 0. We already talked about, but it's kind of related to this. There it is. Yeah, someone said that the infinity flips, and that's absolutely true, right? So because p is greater than 3, check what this is, right? If p is greater than 3, if it's 4 or 5 or 6 or 7 or something like this, right? 1 minus 4 or 5 or 6 or 7, right? Those are all going to be negative numbers. So this is really raised to a negative exponent here. And so really, we should rewrite this as 1 over infinity to the, and we could flip this, right? Because now it's going to have a positive exponent, right? P minus 1 is going to be positive if 1 minus p is negative. And so this will end up going to 0. So 1 over 1 minus p, 0, right? Because 1 divided by an extremely large number goes off to 0, minus 1. And so this does actually converge. And moreover, we can say that it converges to 1 over p minus 1. So converges. And better yet, we can say what it converges to. So this is a bit, of a nice, interesting question here. I'm sure there are some, more things that we should talk about with regards to this. Let's call on Teresa. You have the floor.
I'm really confused on why the the 1 minus p switched to p minus. I think I'm just confused on the concept of it diverging and then converging based on p.
Sure. So, yeah, I guess why we flip this is, right, if you take infinity, and maybe before we get into the specifics here, if you take infinity and you raise it to a positive power, right, infinity squared, right, remember really what this means, and we should probably be a little bit more careful with this in terms of limits and everything, that we're taking a very large number and we're squaring it. Or
So it's
like,
bigger.
yeah, exactly. So it's even bigger. It's still going to be going off to infinity. So I won't use equal signs here. I'll just say it's going off to infinity because, again, you're thinking very large numbers and you're applying powers to them.
Okay.
Now, on the other hand, if you were to take something like infinity and raise it to the negative first power, or infinity raised to the negative second power, well, remember from our rules of exponents here that this is the same thing as 1 over infinity to the first power, or this is the same thing as 1 over infinity squared, or things like that. So when you have a negative exponent, they still behave. Again, you're thinking about very large numbers. So if you take something like a billion and you raise it to the negative first power, right, it would be 1/1,000,000th. You just throw it into the denominator. And likewise, if you do a billion raised to the negative second power, again, you kind of flip it and it ends up in the denominator and then you multiply it by itself. And so when you take very large numbers going off to infinity and you raise them to a negative power, right? They flip, you take the reciprocal of them, and then one divided, exactly. One divided by an extremely large thing goes off to 0 overall. And so really that's what we're doing here is that we're seeing that because this was negative, really it'd be kind of more straightforward if you wrote it in the denominator, and then you would see that it goes to 0.
Does the coefficient not matter of 1 over 1 minus p? Because it'd be 1 over 1 minus infinity.
I mean, still we need to consider this at the end, right? We have this that's being multiplied by our entire function. And so, yeah, it does, I guess for this one here, it just says that it converges. It doesn't ask what it converges to since it's a true false sort of question. So this one is just, true, it converges, but, in another style question, you could ask, what does it converge to? And then you would have to write this.
Okay. But I think I'm just confused on why we know it converges. Because if we plugged in infinity down there, wouldn't it be 1 over infinity minus 1?
Well, you have to be careful what you're plugging infinity in for, right?
Oh, we're plugging 3 in. Okay.
Yeah, we're plugging in infinity for t, right? That's the limit as t goes off to infinity. P isn't necessarily infinity. It's just some number. It could be 4, it could be 5, it could be 7, it could be, 300, right? But yeah, it's just some number that's bigger than 3.
Okay, thank you so much.
Yeah, of course. Any questions coming up in the Q&A, Yuan?
Many people is asking why the final is not negative 1 over 1 minus p.
Yeah, so that would be the same thing
No,
here.
I don't think they have a bracket.
Oh,
They don't have a parenthesis. Have it?
so this would be the same thing. You could write it as -1 over 1 minus p, and that would be the same thing as this here. So yeah, I guess either way, no matter how you write this, hopefully you see that it's not infinity or negative infinity. And so we will all agree that the answer really is that it converges, and that overall the for this true false, we would have true. Good. Any other questions in the Q&A?
No, I think people are just asking this P stuff.
Okay. Let's go ahead and take a look at this. You know what? In fact, I want to talk a little bit about 7.5. And so I'm going to go ahead and, kick this can down the road a little bit. Think about, right, how would you find the antiderivative of this? It's the same sort of steps here. But, right, does this converge or diverge? What's happening to this thing here? Notice that the issue why we have, because you don't see any infinities here, but if you try to plug in 0 for the natural log, that will be an issue, right? So that's where our discontinuity lies. And so think about this one, and I'll go ahead and work on a solution and post it after class here. For 7.5, this kind of brings together all of our sections from chapter 7. And, we stare at them at once as far as how do you know when to do what? And so maybe as is tradition, right, I'll take a quick look at the video notes, the pre-class video notes for 7.5. And you can see that we outline a decent strategy as far as when you're given a problem, an antiderivative, and it just says, hey, evaluate this thing, how do you know what to do? And I think a good thing to start off with is, if you can simplify the integrand, and sometimes this happens, especially for like trig functions and stuff like this, it's a good idea to try to simplify that, right? And so simplifying it, or if you have anything with like square roots of squares, or if there's a way to rewrite it, maybe by multiplying by a conjugate or something like this, this often, has a good outcome to it. Next up is there are certainly some problems out there, right, that we're still using substitutions. So, I mean, U-substitution is not dead, right? I mean, you could certainly use U-substitution, and this is probably the easiest method that we know now, that could possibly show up for quizzes and exams and things like this. And so think about, could you do a substitution? We even had some of these in some like difficult problems. I'm thinking about like integration by parts and stuff like this, where you first did a substitution and then you had to do something else. And then finally, kind of where the meat of this is, try to classify, right, what kind of integrand that you have, right? So talking about, if you have a trigonometric functions, if you have a set of trigonometric functions, you're probably thinking about 7.2, right? How to integrate powers of trig functions. If you have rational functions, right, polynomials divided by polynomials, you're probably thinking about 7.4, right? Partial fractions. Integration by parts is a bit difficult, right? They can look lots of different things. There are lots of different integration by parts style questions. However, some of the classics are like if you have a power of x times e to the x, or really any exponential, or if you have a power of x times sine, or a power of x times cosine, or the hyperbolics, or things like this. Powers of x times, a lot of these sorts of things are kind of classic integration by parts. And then, of course, the maybe most feared one, e to the x times sine x, or like any of the hyperbolics and stuff like that, right? These are going to be ones that kind of wrap around on themselves, right? So this is also going to be integration by parts. So here's some like classic ones. Certainly, if you had something that looked like these, you should be kind of going to integration by parts a little bit faster. But otherwise, right, there are lots of things, even when we talked about like what is the integral of the natural log, that ends up being an integration by parts problem, but it's not obvious at first. And then finally, right, radicals, anytime you have a square root, maybe your mind should go a little bit to trigonometric substitution, right? Certainly there are some that you don't need trigonometric substitution in order to solve, but many of them, trigonometric substitution ends up being the good result. And then, yeah, step 4, sometimes we guess wrong. And this happened even when we were doing U-substitution or integration by parts or things like this, is that sometimes we do just guess wrong. And so at some point you may have to back up and try something else. And don't be afraid to do that. Don't just kind of give up on the problem. I mean, if it is on a quiz or an exam or something like this, maybe do move on and try something else. But if it's not working out for you, just back up, try something else. And with that, we are at 2:40. What we're going to start with next time is looking at all of these, and so before class, I would recommend your pre-class video, since you've already watched the 7.5 videos, is to look through my example 8 here and try to identify what techniques would you use in order to evaluate these out. So that's going to be the last bit. All right, with that, that's all I have for today's class. Thank you everyone for joining. Do have a meeting again, and I need to do a little bit of work before that. So I'm going to set our cutoff at 2:50 for questions and whatnot. So if there are any questions, happy to take them, but I do need to leave by 2:50 to kind of prepare for my 3 o'clock meeting.